Okay. All right, so I kind of tried to organize this with common base rules, so that's the first two. Then a power-to-power rule, parentheses, how to deal with that, and then negative exponents at the bottom. So I've got really 7 different rules down the left column, then kind of another raw, a little bit more challenging example of those with fractional exponents, which is kind of where we up the ante a little bit in Algebra 2. And then I give you the general rule in terms of kind of variables. So, can anyone tell me x to the 7th times x to the 4th, what that would be? Go ahead. X to the 11th, very good. So, the rule there is just to do what? Add them. So, if we go over here to the general rule, you keep the same base, whatever that common base was, x, and you do a plus b. And I say that keep the same base. Can I add something else here for you? 2 to the 3rd times 2 to the 5th. I can't stress enough to keep the same base because I see people in a case like this tell me that that's 4 to the 8th power, and it's not, right? You don't also multiply the bases. You're applying, as far as PEMDAS is concerned, you're applying exponents first. So the rule here is just keep the same base of 2 and then add your exponents. Okay? That would not become 4 to the 8th power, so stay away from that. And really you can see that pan out if you expand 2 to the 3rd power, 2 times 2 times 2, and if you expand 2 to the 5th power, you can obviously see that there are 8 2's total, not 8 4's, correct? Okay. So if you jump in the middle here, what we have to be better at and used to in Algebra 2, because it comes up often, is how to apply these rules when there are fractions. Adding fractions, we all know, is probably like a 5th, 6th grade topic, but one that across the boards through calc they struggle with, because you just, again, you're used to having calculators next to you, and you still do, so you could type that in. But I'm just going to review with you. If you want to add fractions, you need a common denominator. And that would be what here? 12. So we'd have 3 had to get multiplied by 4 to get to 12. So 2 has to get multiplied by 4, and that would become 8 twelfths. And then 1/4, for 4 to become 12, it had to have been multiplied by 3. So the 1 times 3 up top is 3. So 8 twelfths plus 3 twelfths is 11 twelfths. So that's just going to be x to the 11 twelfths. That might be tricky on your calculator, because if I do 2/3 plus 1/4, I'm going to get a crazy decimal. Are you all familiar with how to hit the math button in fraction if you want to bring it back to a fraction? So you can get there, but just good math skill. It's helpful to, know that getting a common denominator is still a thing. All right, our next common base rule. We have x to the 7th over x to the 4th. Who could tell me what that's going to be? Go ahead. You subtract them. Yep, x to the 3rd that's going to be. Very good. So again, if I jump over here, the general rule is going to be x to the a minus b. And then here, if I do 2/3 minus 1/4, and I'll cheat, 2/3 minus 1/4, I'm only doing this for the sake of time. And then again, crazy number, math, fraction, 5 twelfths. So x to the 5 twelfths. Okie doke. The power-to-power rule. Where's Jack? Jack Birmingham. Are you? Do you have a brother? Sean? No. Do you know who that is? Oh, is he? I had him. He's older, right? I'm thinking of the right person. He's older, right?
Second year at Fred.
Second year what?
Academia.
Oh, okay, cool. Jack, what would you do here? What's your gut? Multiply, very good. So this is x to the 28th power. So if I go over to my general rule, it's going to be x to the AB power. A times B, if you want to put a multiplication sign in between those, you may. Now, multiplying fractions is easier than adding and subtracting, right? Because you don't need a common denominator. So when it's 2/3 times 1/4, you just multiply those numerators. 2 times 1 gives you 2. And multiply those denominators. 3 times 4 gives you 12. What you would have to do in a case like this, that it may happen with addition and subtraction, it just didn't happen to come up, is reduce that fraction. X to the 2/12 is x to the 1/6. Now, with parentheses, and what you'll notice, because we talked a little bit about this yesterday, inside these parentheses that are being raised to the 3rd power, or the 1/2 power, or the A power, these are monomials in here. So there's no real need to expand and FOIL. Well, even if you did expand, you wouldn't be FOILing. You literally just have to, in this case, cube each term. So 3 to the 3rd power is 27. X squared to the 3rd power is a power-to-power rule, right? You're raising an exponent to an exponent. You see on the 3, that was a base, a typical numerical base being raised to the 3rd power. So that's just 3 to the 3rd power, 3 times 3 times 3. Whereas x squared is an exponent being raised to an exponent of 3. So you multiply those like we just learned back here. So 2 times 3 is just 6, x to the 6th power. And same thing with the y to the 4th to the 3rd. Anytime you hear yourself saying that string of to the, that's all multiplication. Okay, y to the 4th to the 3rd is going to be y to the 12th. Now, on 4, well, actually, let's jump to the rule just because that's kind of what we've been doing. X needs to be raised to the A power, Y needs to be raised to the A power, and Z needs to be raised to the A power. It looks like that A is being distributed. It's not technically the right word, but if you perceive it that way, that is fine. 4b is a little bit tricky just because a fractional exponent, when you raise 9 to a power, you're essentially letting 9 get multiplied by itself that many times, right? So 9 to the 2nd power would mean 9 times 9. 9 to the 3rd power would mean 9 times 9 times 9. When the exponent's a fraction, that's a little bit different. It's a weird concept to think about 9 being multiplied by itself a half of a time. That doesn't really make sense, right? So we kind of have to stop thinking about exponents and the way that we traditionally do when that exponent is a fraction. That conceptual understanding changes a bit. We will do more on this as the year progresses and kind of what a fractional exponent really means. For now, we're just going to use your calculator. So we'll just take 9 and raise it to the 1/2 power. 3. Here with an x to the 5th power raised to the 1/2, we are still just going to do power to power. So 5 times 1/2 is 5/2, so that's x to the 5/2. And y to the 2/3 to the 1/2, we're going to multiply those exponents, so that's going to be y to the, again, when you're multiplying fractions, multiply those numerators, 2, multiply those denominators, 6, and then just go back and simplify that to 1/3. I would rewrite the whole thing, but I don't have room, so I'm just going to erase and write 1/3. Okay, this whole idea of parentheses, even when there's a fraction inside, we're still sort of distributing that exponent to every single term inside, including those constants. That's what people forget about the most. So make sure you do 2 squared, which is 4. X to the 3rd squared is going to be what, Faye? Where's Faye? What's x to the 3rd squared going to be? We're not squaring 3. Because 3 is the exponent. 3 is not the base. X to the 6. Very good. And that's a key thing to differentiate between a very common mistake, Faye, so nothing to be embarrassed about. Is it a base that I'm squaring? 3 squared would be 9. Or is it an exponent on a term that's being squared? And that's where the power to power rule comes in. 3 squared is what, Natalie? 9. And Eric, y to the 5th squared is going to be what? Nope. Again, I'm not squaring the 5. I'm squaring y to the 5th. Y to the 10th. Very good. Okay, on the general rule here, it's just x to the a over y to the a. And then here on 5b, x to the 3/5 to the 1/2. What's that going to be, Owen? To the 1/6, you said? Where'd you get that from? We have x to the 3/5 to the 1/2. So just, where'd that come from? X to the 3/10. Very good. And on our denominator, 4 to the 1/2 power. Get your calculator out for that. Mike, what should that be? Where's Mike? Who's Mike? 2. Very good. And then y to the 1/2 is just y to the 1/2. And negative exponents. Okay? Does anybody know, remember, from Algebra 1? No final answer should have a negative exponent in it. So how would you rewrite x to the negative 6th to rewrite it as an expression without a negative? Right. In this case, yes, not always. If it's already a fraction, it may not then be one. But if it's currently in a numerator, which this is technically over 1, so if it's in a numerator, when you move it to a denominator, that counteracts the creation of the positive exponent. So this is just going to be 1 over x to the positive 6. Sierra, did you have a question?
Oh, yeah.
Okay, good. So this one again is in a numerator. So to make that exponent, which is currently a negative 2/3, we need to make that a positive 2/3. We do 1 over x to the 2/3. I actually would prefer to do 7b before 7. So 7b, it's already 1 over. So the negative exponent is already in the denominator, so to counter that and make it a positive exponent, we have to rewrite it in the numerator. So that's going to be y to the positive 3/4. Now, 7 is different because it's got something in the numerator other than 1, right? This x, does this have a negative exponent on it? No, so we are not touching it. It's in the numerator, it's staying in the numerator. This is the one with the negative exponent, so this one has to move up to the numerator. So really, the numerator is going to still contain that x, and a y to the positive 2nd power is going to accompany it. Now, there's nothing left in the denominator, so we could placehold that with a 1, but usually we don't leave things as over 1, so we can leave it like this. It looks just cleaner. Okay? And, oh boy, question of the century. Jack Taylor, anything to the 0 power equals? I'm going to audit your work. 5 to the 0 power. 1. 372 to the 0 power. 1. We're so used to 0 just making everything 0 because of multiplication. In reality, the answer is 1. Was this the class where I asked you? No. What 17 divided by 0 was? No. Do you know what it is? Undefined. Good. That a lot of people say, oh, it must be 0, right? Because we're so used to 0, just making everything 0 for us. But not with exponents and not when you divide by 0. Can't divide by 0. It's undefined. Okay, on the back. This is just practice, often with multiple properties going on. So we've got obviously the parentheses here. So everything in here, each of these three pieces, the -3, the x term, and the y term, all need to be squared. What is -3 squared? What's -3 times itself? +9, yes. So that negative, and we did talk about this yesterday, right? Was it this? Oh yeah, we did. See, I have my notes from yesterday. We talked about whether or not that negative is in those parentheses getting squared itself, and it definitely is in those parentheses. So we square that, we get +9. On the x term, x to the 4/5 has to be squared, so that's a power to power rule. 4/5 times 2 is just 8/5. If you wanted, you could put that 2 over 1, so you could go numerators times numerators and denominators times denominators. But 4/5 times 2 is just 8/5. 4/5 times 4 is just 16/5. Okay? I think sometimes we overthink that multiplication. And then y to the 3rd squared is y to the 6th. Power to power, we multiply. Here we're kind of multiplying. These are not polynomials, so there's no distributing going on. It's just -7 times -2 is 14. What is x times x to the 5th, Haley? X to the what? Oh, that's a good question because it hasn't come up with. What is technically the exponent on something if you don't see it? 1. So if that helps, can you tell me what it is now? X to the 1st times x to the 5th? Yeah. Yep. You treated it like it was a 0, right? Because you didn't see anything? Okay, so now we know. If it was a 0, if it was x to the 0, what would it be? It would be 1, and so you really wouldn't even be written there. Gotcha. Okay. Oh, you did 5 times 1? Gotcha. And then on y squared times y to the 1/3, we're multiplying common bases. This is not a power to power rule. It's a common base with a y to some power being multiplied by another y to some power, so we should be adding those. When you add 2 plus 1/3, it is 2 1/3, but you will never see mixed fractions. So you would either, let's think back to elementary school or middle school, I guess. 2 1/3. If you manually change that to a mixed fraction, do you remember doing 3 times 2 is 6, plus that 1 is 7/3? Okay? Or on your calculator, you could just do 2 plus 1/3, get a crazy decimal, and then hit math fraction and get your 7/3 that way. So y to the 7/3. Okay, on 3, with division, just like with the multiplication, you kind of do the constant times the constant here. On 3, you're going to do the constant divided by the constant. What is -35 divided by 5? -7. And then when you do your common base division here, we're supposed to be subtracting those exponents. It's always the top minus the bottom. So what is 2 minus 6? -4. That's not something we're going to be able to leave there, but for step 1, we're good. And then on the y terms, same thing. Top minus the bottom. You have to be careful here because the double negative is going to come up. A 4 minus a -8 is going to turn into 4 plus 8, which is 12. So y to the 12th. So the only thing we now have to address further is that negative exponent. This is the only piece that has a negative exponent. That's the only piece that has to move to the denominator. A lot of people unintentionally just, I don't know, what the draw is. They'll move that negative 7 as well. That negative 7 does not have an exponent at all. Technically, it's a 1, so it's positive. This is the only piece with a negative exponent. So we will leave the negative 7 and the y to the 12th up top. And then the denominator will be x to the 4th. Okie doke. So you start to see a couple layers of rules. This one, we're going to work kind of from the outside and hit that parenthesis rule first and raise everything to the negative third power. So 4 to the negative third is just going to be 4 to the negative third. We'll handle that negative exponent in a minute. X squared to the negative third is x to the negative 6th. And on our denominator, y to the third to the negative third, power to power, multiply y to the negative 9th. So that's layer 1, handling the parenthesis. Layer 2 is going to be getting rid of the negative exponents. Every single term here has a negative exponent, yes? When every single term has one, every single term needs to switch locations. The y on the bottom is going to come up top as y to the 9th. And the 2 on the numerator are going to move to the denominator as 4 to the third and x to the 6th. And you can type in 4 to the third and get that whole number if you'd like. If not, that's fine. Okay? Number 5 asks you, what is the value of a that would make this an identity? So essentially, we need to simplify this down into just x to some power, and whatever that power is going to be the value of a. So on our numerator, power to power means multiply. So 3 times a half is 3 halves. So that's going to be x to the 3 halves. On the denominator, what's the rule I should be following, Sierra? Oh, you're not the Sierra I was talking about. Sierra with an S. Oh, it is? How are you there? You're Sierra O? Where's Owen? Aren't you Sierra too? Okay, you're who I'm talking to. She's Sierra with an S. You're Sierra with a C, aren't you?
I'm Sierra.
Your last name's Randon? Oh, you guys flipped on me. Okay. That was probably clearly not intentional. Okay. So Sierra across the room. I'm sorry. What's the rule on the denominator? What should I do with those exponents? Add, subtract, multiply, divide? Add them, yep. So negative 2 plus negative a half is going to be negative 5 halves. So there's step 1. Now what's the rule on these common bases that are being divided? What do I do with those exponents? Vinny? Vince, you're not Vinny, you're Vince. You subtract, correct, sorry about that. 3 halves minus negative 5 halves is going to be 3 halves plus 5 halves, which is 8 halves. 8 halves is just a fraction that we can reduce into 4. So what's the value of a? 4. Okay, the last section here at the bottom, you're just kind of filling in the blank. So thinking almost backwards. What would this other term need to be? 2 times what was going to give me 6? 3. So there's my coefficient. X squared times what is going to give me x to the 5th? Raise your hand if you can tell me that. X squared times what? Go ahead, Angelin. X to the 3rd. Yep. Very good. So she was thinking, okay, that's the common base rule. In order for x squared to become x to the 5, it has to be multiplied by x to the 3rd. You see that? Questions? We're good? And on 2, actually, let me go to 3. Do you see how both of these have an x minus 2? Okay? One of them is getting multiplied by a 4x squared. So it's almost like I'm taking that x minus 2 and I would multiply it by a 4x squared. And then I would multiply it by what to become this? X minus 2 times what would make negative 9 times x minus 2? Don't overthink it. It's as simple as it looks. What did you say? You're all afraid to say something. Would be negative 9. Rather than distributing just one term, it's almost showing a distribution of a binomial. So 4x squared gets multiplied by that x minus 2, and then a negative 9 gets multiplied by an x minus 2. Okay? So you'll have some fill in the blanks like that in your homework. So here is your regular homework coming around. Have a great weekend. I'm setting all 12 right here. If I counted wrong, it's not my fault. Have a good weekend.